last lecture we were trying to cover up relook at multivariate calculus relevant for thermodynamic such as in this course. We will continue this exercise. So, let us assume functions f is a function of x y, let us say f1, where y is dependent on x and z. Okay. So, in other words, f is function of f x f2 x z or some function f3 x z. Okay. So, the reason we are considering such a complicated function, because typically thermodynamic functions are not just f is equal to x and y, where x and y are independent. So, most of the time we have more complicated functions. Now, in this case, if you want to find out partial derivatives such as f and del x, it has no meaning until you specify what is fixed. Okay. So, for example, del f by del x at constant y is del by del x f1 x comma y, okay, or del f by del x at constant z is del f by del x, okay, because this is s and z, we are going to consider f3 x z. So, clearly in this case del f by del x y is not equal to del f by del x z. So, what is the relation between these two? Okay, so, we are going to consider a differential of f can be written as del f by del x z at constant z multiplied by dx plus del f by del z at x. Okay. Now, this can be further differentiated such that del f by del x at y is del f by del x z, and this is written as del x by y, okay, plus okay. So, this is of course going to be 1, and thus you can write del f and del x at constant y, del f by del x at constant z plus del f by del z constant x, del z by del x at constant y. So, this is the relation between these two partial derivatives. Okay. So, we can further continue, particularly now considering f as a function of more variables, something which is what we are going to encounter in thermodynamics. So, let us assume that f is a function of x1, x2 and so forth. In that case, df can be written as summation of partial derivatives of f with respect to xi, where I is equal to 1 to n at, and this derivative is at keeping x1, x2, xi minus 1, xi plus 1 till xn constant. Okay. So, this is something which we can write the differentiation or differential amount of f in terms of the summation of the partial derivatives. Okay. We can integrate this also, all right. So, if you integrate this from x1 zeros to x1, then we can get something like this minus f of x1 0, x2 0. Okay. This is nothing but summation of I equal to 1 to n integral across the path we are going to take del f by del xi, x0 is not equal to xi dxi. Now, remember that the left hand side is independent of the path, but this right hand side the expressions will depend on which path you're going to take. So in order to illustrate, we will take some example. So let us consider plot y against x, where we have x0 y0, okay, and somewhere here is x1 y1. So the easiest path we can consider is basically composed of straight line segments. Okay, so what we can do is we can consider straight lines such as this. Okay, this is one path composed of two line segments. Let me say this is gamma A, and there is another one from here till here. So in this case we are keeping x constant, and in this case we are keeping y constant. This would be another path composed of two segments, and let me say this is gamma B. Okay, and so what we are interested in is delta f. Okay, so delta f is, in this case, since it's a function of two variables, so this is going to be fx comma y. So this will be x1 y1 minus fx0 y0. Okay, so based on this definition which we have put it here, this delta f can be written as del f del x y dx plus del f by del y x dy. Okay. So now, since we can consider two different paths, we are going to derive this expression for two different paths, and you can clearly see that the expressions are going to be different. Okay. So let me consider this A. All right. So this will be x0 y0 to x1 y0, and finally x1 y1, and this is going to be x0 y0 to x0 y1 to x1 y1. So just to make this clear, so this is going to be 0 x0, and this is going to be x1, this is going to be y0, and this is going to be y1. Okay. So let me just further write it now expression. Now this is going to be for gamma A path, okay, del f by del x. In this case y0 is constant, so this is nothing but y equal to y0 dx plus, so this is part 1, and similarly you can also integrate x0 y0 to x1 y1, sorry y0 del f by del y x dy. So this is going from x0 y0 to x1 y0 plus, so this is again plus here, plus you have another path, another line segment from x1 y0 to x1 y1. So it's going to be x1 y0 to x1 y1 del f by del x. So this is basically again y is equal to y dx. Since x1 is fixed and y is variable, okay, which means this term is going to be 0 considering that x is fixed, and the second term is going to be again x1 y0 x1 y1 del f by del y x dy, where x is nothing but x1. Okay. So what I did was, you have two parts or two partial derivatives. So this is basically the partial derivative integration over first line segment. This is the derivation over the second line segment. in the first line segment y is equal to y is constant. So, the first derivative is this one, and the second derivative, this one, since is y is constant, this should be also 0. Okay. And similarly, this for the second line segment. So, when you simplify this expression, delta f turns out to be x0 x1. Okay, since y is constant here, I can simply write del f by del x, y is equal to y0 dx, plus this one, which is going to be, since x1 is constant, I can simply write y0 to y1 del f by del y, x is equal to x1 dy. Okay. So, this is one expression. Now, if you had used gamma b, you could show that del f is x0 x1 del f by del x, y is equal to y1 dx plus y0 y1 del f by del y, x is equal to x0 dy. Okay. So, the constants are different. Okay. So, this is a simple way of finding out changes in the functions using paths which are broken into different line segments. Okay. So, we are going to continue this exercise now, and now we are going to look at Euler theorem for homogeneous function. Okay. Now, this is an important component of classical thermodynamics. So, let us make a comment here that thermodynamic function and its derivative are either extensive or intensive. Okay. So, this is something which we observe, that all these functions are either extensive or intensive. Okay. That we have already defined. Now, mathematically, a function which satisfies a relation such as this for all values of x are called homogeneous function of degree 1. Okay. So, this is a typical extensive property of which we know from thermodynamics. Okay. So, the intensive property would be a homogeneous function of degree 0. Okay. So, that means the function that is homogeneous of degree 1 with respect to variable, let us say x1, x2, xi, and homogeneous of degree 0 with respect to variables y1 till yj has the following property, has the property that you can write the following as this. Okay. So, what I did basically nothing but the lambda which is multiplied here in this variables have been taken out and multiplied the whole function by a lambda. That is what basically nothing but Euler theorem. Okay. So, this is true for any x1, xi, y1, yj. Okay. Now, thermodynamic function are homogeneous function of degree 1 with respect to extensive variable and degree 0 with respect to intensive variable. So, this Euler theorem basically provides a link between its function as its derivative, and we are going to show that we are going to prove that. Okay, so let us consider again this function which we know f, okay, and just take its derivative del f lambda x1 till lambda xi and y1 till xj, or y1 till yj with respect to lambda. So, we are taking a derivative of f with respect to lambda. Okay. Knowing this Euler theorem, we can write this expression as del lambda f x1, okay, till y1 and so forth. Okay. Now, this is with respect to lambda, thus this is nothing but f of x1 xi comma y1 till yj. All right. So, this derivative of f with respect to lambda is nothing but simple function f. Now, you can also rewrite this expression as follows. Okay. This is nothing but based on the differential information, this is nothing but del f lambda x1, okay, del lambda x1 del lambda x1 del lambda plus and so on until you have this del f lambda x1 lambda xi, okay, del lambda xi del lambda xi divided by del lambda. So, this is nothing but xi, okay. So, this turns out to be nothing but x1, okay. So, what we have is and similarly that one is for x I. Now, this is just a multiplication of lambda, lambda can come out here, and similarly f can be written as f of this can be written as lambda times f, and lambda lambda can cancel. So, this is nothing but equivalent of saying x1 del f x1 xi y1 yj divided by del x1 plus xi del f again there is del xi, okay, and this is nothing but f from this term. So, this gives us basically Euler theorem for homogeneous function in this form, okay. So, this is basically because x1 to xi are homogeneous function of degree 1. Now, having derived this expression, we can also apply it to thermodynamic functions. So, let me just try that for internal energy. So, if you consider, so the objective now is to apply to, let us say, u as a function of u, v, n1, n2 and so forth, okay. Now, these all are extensive variable. So, this is all homogeneous function of degree 1, okay. So, with respect to all the variable. So, in that case u can be written as, u is nothing but f, can be written as x1 is s del f by del s, keeping all of the variable constant, v plus v del u by del v, keeping all variable constant, plus summation ni del u by del ni, keeping all other variable constant. Okay, so now also this f should have been u, so we are going to write it here u, okay. Now, what is del partial derivative of u with respect to s is nothing but t. What is the partial derivative with respect to u, partial derivative with respect to v? This is nothing but, if you look at the first law of thermodynamics, you can derive that this is nothing but minus p, and this is nothing but mu I. So, we have now a relation u is equal to Ts minus Pv plus summation Ni or mu I Ni. Okay. So, we have now got an equation which is Euler integrated fundamental equation. Okay. Okay, so this is based on the very simple mathematics, and this expression are going to be extremely useful to derive something called Gibbs-Duhem equation, which we are going to talk in the next lecture. So, with that I am going to stop and we will see you in the next lecture.